So we now take a look at gases. We look at gases separately from our other phases of matter because gases have a number of properties that are unique to them. What are some of those things that are unique? Well, it starts with just their physical state. Gases have no definite shape or volume. In other words, they take on the shape, they take on the volume of whatever container they're put in. And because of that, unlike other phases of matter, gases are also compressible. If you change the size of the container that the gas is in, you, know, you can still have the same amount of gas. You just have to make it smaller. So you do that by compressing it. When you mix gases, they're very easy to mix. We get homogeneous mixtures. And part of this is because they have a very weak attraction to neighboring molecules. Or we sometimes say that whatever the neighboring molecules are is irrelevant. And this is not the case for liquids and solids. As you'll learn in a future chapter, whether two liquids or a solid and a liquid are able to mix very much depends on what the compounds are. But for gases, because the attraction between molecules is so weak, what those molecules are doesn't matter. Gases also exert pressure on the container that they're in. And finally, when we're talking about gases, it's mostly empty space. On average, typical gas might take up about 1% of the actual volume, the gas molecules. So a lot of space in between the molecules, which leads to why the identity is irrelevant, why there's such a weak attraction. Now, when we talk about pressure, that's something we can measure, and we need to define our units that we can pressure. Pressure is a measurement of the force that acts on a given area. Now, force is usually in newtons, and area, in meters squared. And so this unit for pressure, newtons per meter squared, is equal to 1 Pascal. Now we actually use a number of different units for pressure. We have millimeters of mercury, we have torr, atmospheres, and pascals. And we'll see in a moment, we also have, given that what we know we can do with any SI unit, we can put a prefix on it. We have kilopascals. And so what we would refer to as standard atmospheric pressure is what we can use as a unit conversion to go back and forth between any of these units. So standard atmospheric pressure we consider to be 1 atmosphere. In both torr and millimeters of mercury, that would be 760. In pascals, 101,325. or dividing that by 1,000 gives us 101.325 kilopascals. But what we're going to be most interested in this section are our gas laws. And our gas laws give us the ability to relate pressure, volume, temperature, and N, or number of moles. And we start out with a bunch of simpler laws that look at different combinations of two of these. We work up to a combined gas law, which looks at pressure, volume, and temperature. And then eventually we get to the ideal gas law that is going to include all four of these terms. Now, depending on how strong your math skills are, you can typically use the ideal gas law and or the combined gas law to derive the rest of the equations. But we will go through each of them. Now we're going to be making some assumptions. How a gas behaves, its physical behavior, differs depending on the gas that we're looking at. But we're going to assume for the rest of this chapter, the rest of these calculations, we're going to assume what we call ideal gas behavior. What is ideal gas behavior? It basically means that a gas follows the ideal gas law. The ideal gas law we can just show very quickly here. We'll come back to it later. PV equals nRT. So if a gas obeys that equation, PV equals nRT, then we consider that to be an ideal gas. And as I said, for the purposes of this chapter, we're just going to assume that the gases we're looking at do. Now this equation here that I've just put up is known as the van der Waals equation. And this is kind of more of a real life situation. You can see that the right side of the equation matches a number of moles times R, which is a constant, times the temperature. But then we get these extra factors that we add to our pressure and volume terms. And those are what change this from an ideal gas behavior to just any gas. But we're not going to deal with the second equation when we get to the ideal gas law. We're going to stick with just PV equals nRT, as well as some other equations that all assume ideal gas behavior.